simplifying a cos x plus or minus b sin x. The graph of y equals 3 cos x plus 4 sin x does not seem so straightforward to sketch, or if you had an equation like this, for instance, that doesn't seem so easy to solve either. Let's have a look at this graph and see if we can get any clues on how to solve something like this. So here is the graph. It looks like some kind of sine or cosine curve that's been transformed a couple of times. For instance, I could start off with the cosine graph in blue. I could do a translation to move the graph to the right, something like this, and then do a stretch in the y direction, something like this, and you can see the graphs are almost identical. So is there a way of working out values like these, like the 5 here and something similar to this minus 54 here? I could equally have started with the sine graph and then a translation in the x direction to move this peak here to roughly here, and then do a stretch again by times 5 in the y direction. Again, I would have the same graph overlapping the red curve. So instead of sketching this equation, it's far easier to work with this. This is just in terms of cosine. A single trig function makes the whole job a lot easier. Here we've got two different trig functions. We've got a mixture of cosine and sine. Here we only have cosine, a lot easier to work with. So I've got a mixture of cosine and sine terms. This is just in terms of sine, this is just in terms of cosine. And the angle x there, here it is, x. This plus or minus alpha here, this is a translation of the sine graph along the x direction, a translation of the cosine graph along the x direction. And this multiplier r is a stretch in the y direction. So we start off with something in this form, for example, and we have a and b, these are coefficients. A is 3, b is 4. So using this equation we now know the value of r. R is your stretch in the y direction. So you start off with a basic sine or cosine graph and you stretch it in the y direction, and this is your stretch factor. We still need to work out the translation along the x direction, which is alpha. And alpha could be in degrees or it could be in radians. And a combination of these two equations will lead to that value of alpha. And alpha is your translation in the x direction. So let's have a look at coefficients. In this simple equation, the coefficient of cos theta is a, and the coefficient of cos theta here is 5. And because we have a single cos theta term on each side, a is equal to 5. In this equation, we have a single cosine and sine term on each side of the equation. So the coefficient of cos theta here on the left hand side will be equal to the coefficient of cos theta on the right hand side. So I know that a is equal to 5, and for similar reasons b, the coefficient of sine theta, will be equal to 2. So a is equal to 5 and b is equal to 2. Here we have a single term on each side, sine theta, sine theta. The coefficient of sine theta on the right hand side is r. The coefficient of sine theta, so whatever's multiplying with the sine theta term, is 5 cos alpha. So that's telling us the r value is equal to 5 cos alpha. Example 1. We want to write 3 sine theta plus 4 cos theta simplified into just something in terms of sine. So we have theta on the left hand side, we still have theta on the right hand side. The unknown values are alpha and r. Now this is an addition angle identity. Here it is. It's in the formula book. So using the formula and expanding this, we've got these terms in green, but we were multiplying by r, so we have to multiply both of these with r. On each side we have a sine theta term there, and we have a cos theta term there. That's telling us that the coefficient of sine theta, 3, is equal to the coefficient of sine theta here, which is r times cos alpha. So we have this equation. And likewise the coefficient of cos theta here, which is 4, will be equal to the coefficient of cos theta on this side. So 4 is equal to r sine alpha. So here's the long solution, the long version of it. We need to work out r and we need to work out alpha. So if I square both equations and then rearrange each one to make cos squared alpha the subject and sine squared alpha the subject, and then we know a simple identity, cos squared plus sine squared is equal to 1, and if I substitute in for cos squared alpha 9 over r squared, and similarly 16 over r squared for the sine squared alpha, and then multiply by r squared throughout, and then simplify, and then when we square root I'll take the positive square root because r represents the stretch in the y direction and I'm looking for a positive stretch in the y direction, then r is equal to 5. Now we still need to work out alpha, and to work out alpha we're going to divide the two equations like this. We want sine over cos because we know sine over cos is tan, and the r's will cancel, and then I can say that 4 over 3 is equal to tan alpha, and then tan inverse of 4/3 is 0.927 radians. So have your calculator in radians mode. This works equally well in degrees, so if you want the angle in degrees, have your calculator in degrees mode. So now we know r and we know alpha. So we set out to work out r and alpha. We've worked out r, 5, and worked out alpha. So instead of using 3 sine theta plus 4 cos theta for sketching graphs or solving equations, we can use 5 sine theta plus 0.927 radians instead. And this is far simpler to work with a single trig function than to have these multiple sine and cosine terms. Now the short solution, r is just Pythagoras' theorem based on these two values. There we go. That's all you do. And sine over cos, so 4 over 3 is tan alpha. And you solve this and you've got your angle, and then just substitute the values in for your final answer. So graphically we can see in red we've got the original curve, 3 sine x plus 4 cos x, and in blue we're starting off with the basic sine graph. I've done a translation in the x direction, that's where that 0.927 radians came from. This whole graph is in radians, and then a stretch in the y direction, and you can see both curves are exactly the same.